Okay, good morning to all. Today we will discuss about first law of thermodynamics. First, what is the first law of thermodynamics? Then after we are applying the first law of thermodynamics for a system, different types of system, non-flow system, flow system, and isolated system, and simple problems, and what are the findings of first law of thermodynamics and limitations. This one we will discuss. The You can see the brief syllabus also are given. First law application for closed system undergoing cyclic process and undergoing individual state change. Joule's experiment, perpetual motion machine of first kind, and apply application of first law of thermodynamics and non-flow and process, and corollaries means findings and limitations of first law of thermodynamics, and some simple problems for flow process, application of first law of thermodynamics, flow process and non-flow process. Before that, what is first law of thermodynamics? Up to thermodynamics emerged as a science, and the first steam engine is introduced in 1697, and full-fledged working of the steam engine came to the picture in 1712. Law of conservation of energy. The energy neither created nor destroyed. It can change one form to another. So in the statement, it is not useful for us for designing the systems. Some examples I will give. Based on the example, we will develop the equation. Suppose some mass, it is available at some altitude, having the potential energy. Head difference is there, means potential energy. But it is not moving, so there is no kinetic energy. Kinetic energy is 0. The potential energy is 10 kilojoules. Kinetic energy is 0. Now the mass is moved some distance, then potential energy is reducing, head is reducing, means automatic potential. Whatever the energy reduced, that you will convert as a kinetic energy. This potential energy reduced from 10 to 7, kinetic energy increased from 0 to 3. So here we can write first law of thermodynamics, energy in equal to energy out. Initially having energy, potential energy is 10 kilojoules, kinetic is 0, total 10. At final, after completion of the movement of the mass, the potential energy is 7, kinetic energy is 3, total 10 only. The next example. Suppose in home, continuously we are getting solar energy. Walls will reject some heat, it's come. Then remaining what it happens, suppose 15 kilojoules of energy is coming in the home. Some 3 kilojoules of energy is lost through the walls. It's fully insulated also, some loss will take place. Then whatever the remaining energy is the accumulation of energy inside the room. Inside the room, heat temperature is increasing, accumulation of energy. So energy in is 15 kilojoules, energy out is 3 kilojoules. Remaining is change in energy of the room only, 12 kilojoules, accumulation of the energy inside the room. One more, suppose insulated vessel is there, then we supplied electrical energy through the resistance. How much energy we are supplying, that much energy will convert as a change in energy. The liquid heat will increase. If we fill with liquid, the liquid heat will increase. Or if we fill with air temperature will increase. So energy in, how much is there? Why? Because it is insulated, we are assuming. So there is no heat loss. So total will convert as a change in energy. So based on these examples, we can conclude we can rewrite the first law of thermodynamics from the law of conservation to another form. Total energy entering to the system minus total energy leaving the system equal to change in total energy of the system. Total energy entering minus total energy leaving equal to change in energy from this. So this is sufficient. But because this is one form we rewrite. The common form, energy balance, energy in minus energy out equal to change in energy. If there is no change in energy, 0, energy in equal to energy out. And we have different types of the energy transfers are there. Closed system means only heat energy will transfer, only mechanical energy will transfer. If open system, with mass, some energy is entering through the imaginary boundary. With mass, some energy is leaving. So three forms of the energy transfers are there. So based on the energy transfers, we want to rewrite the sorry, we want to rewrite the um, first law of thermodynamics for closed system, isolated system, and open system. Okay, the importance of writing first law of thermodynamics equation for closed system, open system, isolated system. By different types of the energy transfer. Suppose closed system undergoing cyclic operation, because these all are statements. The only one scientist developed the evidence for the statement is Joule. That's why every time we are discussing Joule's experiment. Closed system undergoing cyclic process. What is the first law of thermodynamics? From his experimental results, the statement is coming to the picture. He selected one vessel filled with liquid. Initially, he filled water only. For measurement of temperature, he used thermometer, mercury thermometer only, because his experiment in 1849. So, mercury thermometer only. This stirrer, he inserted one stirrer connected through pedal wheel with the counterweight. Once this counterweight is moving, means stirring operation will occur inside the vessel. We know once we are doing stirring means automatically temperature rise will occur in the inside the vessel. So this is his experimental setup. What he did, he initially selected some weight and some length of travel. Every time lowering lifting of the weight, automatically the by lowering lifting of weight, whatever the effect is coming, the total effect on the system we are doing. What is the effect? We are producing work, not producing. We are supplying work to the system by stirring operation. It will generate heat. How much work is supplied? We can calculate load into distance, W into Z. How much heat is generated? We know temperature is initial temperature we can measure. Mass we know, specific heat of the water we know 4.2 kilojoules per kg Kelvin. Then you can calculate how much heat is generated. So first what is the, he tabulated what is the work. So it is the first process. By work supply some heat is generated. In second process what he is doing, whatever the heat generated is removing that heat by providing any air ventilation or by cooling system. Initially it is a insulated vessel. So the second process is whatever the heat generated, that much of heat only is rejecting. Then we are reaching the initial condition, again he is continuing his cyclic operation. Okay, cycle is completed. So by this operation, he tabulated how much work is supplied and how much heat is removed in two processes. First, he conducted experiment for liquid means water, especially first we conducted experiments of water. For different conditions, he changed different loads, he changed different distances. Then work input he changed, then he tabulated. Then after he changed liquids also. Different types of the liquids he selected. Different viscosity liquids he selected. And again he tabulated work input and heat. Surprisingly, from his experiments, what he is found, whatever the work he supplied, the summation of all work interactions for the cyclic operation is directly proportional to the summation of the heat generated. Heat interactions. So, cyclic integral of work input is directly proportional to cyclic integral of heat input. Then we remove the proportionality limit and introduce Joule. Then 1 Joule we know in SI units is 1 Newton meter per Joule. In CI units we know 426.7 kilo kg Fm by kilocal. Generally we are following SI units. So summation of all heat interaction equal to summation of all work interaction. From his experiment in cyclic operation, whatever the heat interactions are taking place, total summation of heat interaction equal to summation of work interaction. Cyclic integral of dou Q equal to cyclic integral of dou W. This is the first statement of first law of thermodynamics. Closed system undergoing cyclic process. So there is no accumulation of the energy. Whatever the heat we are supplying in cyclic operation, total heat is converting as work. One example, you can write summation of heat inputs equal to one problem will solve. some heat interaction is there. Q1 224 kilojoules, Q2 20 kilojoules, Q3 minus 200 kilojoules, Q4 37 kilojoules. At 4 points of work also is there. W1 50 kilojoules, W2 40 kilojoules, W3 75 kilojoules. Find the fourth work interaction. Summation of all heat interaction equal to summation of all work interaction. Simple. You apply. Determine the fourth. First three are work done by the system. Last one is work upon the system. So summation of all heat interaction equal to summation of all work interactions. Next one. First law applied to a closed system undergoing a change of state. Individual process. For cyclic operation, summation of all heat interaction equal to summation of all work interactions. As from the Joule's experiment. The evidence is developed by the Joule experiment. Suppose closed system, suppose I selected cylinder piston arrangement. Cylinder and piston filled with some gas fluid. We are supplying heat. Then this fluid will initially having the some pressure and volume. Once we supplied heat, automatically the piston will move from state 1 to state 2, having the final pressure and final volumes. Okay. So whatever heat we supplied, suppose it is an insulated one, closed system, you know all walls are the fixed walls, one is movable wall. So volume is changing, mass is not changing, controlled mass. Only energy is crossing the boundary, heat we supplied, automatically expansion of the fluid will take place and piston will move from the state 1 to state 2, having some other pressure. Here, whatever the heat you supplied, total heat will not convert as a work, no doubt at all. Some accumulation of the energy will take place, means the energy of the fluid will increase due to the accumulation. Change in energy will occur, you can see. The change in energy will occur. Heat supply means work done equal to change in energy. Energy, absolute energy we don't know. What is the change in energy? Some change in energy will take place by supply of the heat. It is generating some work. So, first law of thermodynamics, for individual process, heat supply means work done equal to change in energy. You see, heat supply is a path function. Work done also path function. But the change in energy is a property, means point function or path function, first question mark. But for that we are developing one small derivation for evidence. Energy is a path function. So the change in energy is a path function or point function. If it is point function, it is a property. We can use for describing the condition of the system. If it is a path function, okay, no problem. By the process, the value is changing. Suppose I selected from state 1 to state 2, I want to move by process A. Cyclic operation means again I am moving state 2 to state 1 by process B. Then I am completing one cycle. Then you write the first law of thermodynamics for cyclic operation and individual process. The first law of thermodynamics for cyclic operation, summation of all heat interaction equal to work interaction. So two process only, dou Q process A plus dou Q process B equal to dou W process A plus dou W process B. Next, apply first law for the change of state to A and B. We get individual process. Heat supply minus work done, dou Q at process A minus dou W process A equal to change in energy at process A. And again process B also like that only, dou Q process B minus dou W process B equal to change in energy at process B. Then you add to second and third equations, final equation you are getting. Already by application of cyclic operation, dou Q process A plus dou Q process B equal to dou W process A plus dou W process B. Then we can cancel this two. Change in energy at process A plus change in energy at process B is equal to 0. Then change in energy at process A equal to change in energy at process B. The magnitude not changed, direction only changed. Because one is forward, another one is reverse direction for application of cyclic. So change in energy is a point function. It is a property. It is not a path function. I think with this derivation we can conclude this one. And then after we can The change in energy contains internal energy, kinetic energy, potential energy, chemical energy, so many energy in molecule level. But it is a closed system. So there is no velocity, there is no mass movement, means there is no velocity, there is no elevations. Then we can neglect that kinetic and potential energy. The change in energy means change in internal energy only. Because internal energy is function of temperature. I am supplying heat means some function of temperature only. So automatically internal energy may increase or decrease. So heat supply mass work done equal to change in internal energy. Dou Q equal to du plus PdV. This one we can use for determination of the heat transfer in different processes. I already mentioned from the Joule's experiment, internal energy is mainly a function of temperature only. Then first law of thermodynamics for an isolated system. In isolated system, neither energy nor mass cross the boundary. So energy not crossing, mass not crossing means heat interaction, work interaction is zero. Then change in energy is zero. So finally energy is constant. First law of thermodynamics for isolated system is energy of the system is constant. The second statement. Next we will move to the perpetual motion machine of first kind. Okay. Move to the perpetual motion machine of. What is a perpetual motion machine means? It's indirectly, directly it's a violation of first law of thermodynamics. So because I already mentioned, first law of thermodynamics is a statement. Only one experimental evidence is available, that is the Joule's experiment. So some scientist group opposing the first law of thermodynamics, they took the R&D funds and they developed one engine which can be violate the first law of thermodynamics. So anywhere perpetual motion mission is coming to the picture means violation of thermodynamics. If one means it is a violation of first law of thermodynamics. Just we will see the construction of the engine, then we will get the clear idea what are their assumptions, what is how it is violating the first law of thermodynamics. You can see they selected only Rankine engine. Other engine they are not selected. They selected Rankine engine. Rankine engine construction we know: pump, boiler, turbine, condenser. Low pressure liquid is pumped to the high pressure boiler by using the circulating pump. Then only liquid we are pumping to the boiler. In the boiler, we are supplying heat by the nuclear energy, by fossil fuels, or by solar, by biomass. Any method we are supplying the heat in the boiler. Then, by supply of the heat, this liquid is converted as a steam. That high pressure, high temperature steam is expanding in turbine. It is producing the mechanical energy. That mechanical energy is shaft is connected to generator. It is producing the electrical energy. This low pressure steam directly we are not pumping to the boiler. Why? Because the specific volume is 1000 times difference. Whatever the energy we expanded, so total energy again it will consume for compress the steam from low pressure to high pressure. That's why we are rejecting the heat at condenser. This low pressure steam will convert as a low pressure liquid. That liquid again by using pump we are circulating. This is the Rankine cycle. The cycle is same, but here the scientist group what they proposed, instead of external heat supply from the generator, part of the electrical energy is using for supply of the heat in the boiler. Part of the electrical energy they consider for supply of the heat inside the boiler. Very good. This part of the heat is supplied to the boiler. Then there is no external supply. Initially we are supplying the heat in the boiler from external source, any type of heat. After a system reaching the steady state, then we will stop the supply from the external source. Whatever the electrical energy generated by the generator in the cycle, part of the electrical energy we are using for boiler. This is their proposal, their construction of the engine. Then what is the violation? You see here in this cycle where the energy input. there is no energy input. First law of thermodynamics for closed system, open system, whatever the system, energy in equal to energy out, or energy in minus energy out equal to change in energy. That's all, nothing else. Here there is no energy in. Up to reaching steady state only we are supplying energy. Then after there is no energy in. So if there is no energy in, what happened? You can see there is no energy input. Without energy input, they are producing work output. How it is possible? If I am spending something, then only we will produce the some useful one. Without spending anything, how we can produce? So it's violation of the first law of thermodynamics. Not only work, in the condenser also heat rejection is there. Without energy input, continuously we are producing thermal energy, continuously we are producing electrical energy. So it's a fully violation of first law of thermodynamics. First law of thermodynamics is a basic statement: energy in equal to energy out, or energy in minus energy out equal to change in energy. So after maybe 10 years or 20 years of working, they accepted a violation of first law of thermodynamics, practically not this. Why we are teaching this one in thermodynamics subject means energy balance is the first criteria for designing of the system. For motivation purpose, every time we are explaining the perpetual motion machine of first kind. Next, heat transfer in various non-flow process we can calculate. I already heat supply minus work done equal to change in energy, or heat transfer equal to work done plus change in internal energy. Change in internal energy we know MCV delta T, work done PD. Just I am applying based on the process. I will apply the equation and I can derive the heat transfer in different process. Suppose constant volume process. The first process volume is constant. If volume is constant means there is no work done. Area under PV diagram, P into change in volume, PdV. There is no change in volume means there is no work done at a closed system at constant volume process. Work done is 0. The change in internal energy we know MCV T2 minus T1. So in constant volume process, whatever the heat we are supplying, total heat will accumulate as a change in internal energy. Okay. Next. Constant pressure process and equation is constant volume heat transfer MCV delta T. Constant pressure means MCP delta T. Then here we derive the relation between the CP and CV. Work done equal to pressure into change in volume, change in internal energy MCV delta T. So you substitute both change in internal energy MCV T2 minus T1. Work done pressure into change in volume. You take pressure inside. P1 equal to P2, then for simplification purpose P2 V2 minus P1 V1, convert into MRT, PV equal to MRT, then MR T2 minus T1. Finally MCP T2 minus T1 equal to M T2 minus T1 CV plus R. You can cancel this both. And CP equal to CV plus R, CP minus CV equal to R. Specific heat at constant pressure process always higher than the specific heat at constant volume process. So whatever the heat required at constant pressure process always higher than the constant volume process. From this derivation we can conclude. Next, isothermal process. Here temperature is constant. If temperature is constant means change in internal energy MCV T2 minus T1. Temperature is constant, the change in internal energy is 0. Heat supply equal to work done. Then heat supply equal to P1 V1 ln V2 by V1. So from this equation we can conclude that in isothermal process, whatever the heat we are supplying, total heat will convert as a work. There is no accumulation of energy. It's the best process. But in practical, we are not using in isothermal process. Why? Because it is a slow process. I want to cool the water from 20 to 0. It is easy. Less time it will consume. But 0 water to 0 degrees ice means temperature constant. It will take more time. Time consuming process. But in our cycles, power generation cycles or refrigeration cycles, per hour, per minute RPM, per minute 1500 revolution is the minimum speed. So per minute 1500 cycles are required. So isothermal process we are moving means practically not possible. But isothermal is advantage. Whatever the heat we are supplying, total heat is converting as a work. Next, adiabatic process, you can see adiabatic process. heat supply minus work done equal to change in energy. Change in energy is there. Then Cv into T2 minus T1. Work done P1 V1 minus P2 V2 by. In first unit already we derived. That's why directly I took the equation. Then PV equal to MRT. Then MR into T1 minus T2 by gamma minus 1. Then R by gamma minus 1 equal to Cv. How it came? Cp minus Cv R, Cp by Cv gamma, I substitute, then automatically R by gamma minus 1 we will get a Cv, then MCV T1 minus T2, work done. At change in internal energy, MCV T2 minus T1, both will cancel, heat transfer equal to 0. So, adiabatic process means there is no heat transfer. How the work is taking place? Total change in energy will convert as a work, there is no heat loss. In constant volume process, suppose I supplied heat, total heat will convert as a internal energy, change in internal energy. In adiabatic process, I am doing the work interaction, total change in internal energy will convert as a work. There is no loss to the ambient. And without heat loss, how the process executes? Why? Because in first unit I mentioned thermal conductive are different materials. Any material you select, it has some thermal conductivity, maybe 0.06 something. So, due to fast execution of the process, we can eliminate the heat loss. So, adiabatic process is too fast process. That's why all practical engines work interactions are taking place by adiabatic only. Okay. Next, polytrophic process, same change in internal energy plus work done. MCV T2 minus T1, P1 V1 minus P2 V2 by n minus 1, you can kept common. 1 minus n, Cv plus R by 1 minus n equal to m into T2 minus T1. R you can substitute Cp minus Cv. Finally, we can solve the problem. Gamma minus n by 1 minus n, Cv into m T2 minus T1. So here in computation exam, generally in polytropic process, what is the specific heat equation? Specific heat equation is Cv, specific heat at constant volume into n minus gamma by n minus 1. Okay. Just I wrote the equation. Then we solve some problems. In a closed system means two statements are there. Cyclic process, summation of all heat interaction equal to summation of all work interaction. One point. So there is no accumulation of internal energy in cyclic process. And second one, individual process, heat supply minus work done equal to change in energy. We solve one small problems. In an IC engine, during the compression stroke, the heat rejected to the cooling water. Here they mentioned heat rejected. In a thermodynamic statement itself, heat supplied to and converted as a work. We are supplying heat and converting as a work. So heat supply always positive, work done by the system always positive. Remaining is negative. So here they mentioned heat rejected to the cooling water is 50 kilojoules per kg and work input is 100 kilojoules per kg. Calculate the change in internal energy of the working fluid. Simple, basic, individual process of closed system they given. So, but heat rejected, so Q is negative, minus 50 kilojoules. Work supplied, then work input is a minus 100 kilojoules per kg. If work done by means 100, then substitute heat supply minus work done equal to change in internal energy. Then change in internal energy equal to heat supply minus work done change in internal energy. Then minus 50 plus 100. Then we will get 50 kilojoules. What is the question they ask? Whether it is a gain or loss. It is a gain only. We supplied work and we rejected heat. And ultimately, change in internal energy is a gain. Next, one more problem we can discuss. This is a standard problem asking in examinations, end exams, so 14 marks question like that. A piston and cylinder. That machine contains a fluid system which passes through a complete cycle of 4 processes. So, a piston cylinder arrangement means closed system. It contains cyclic operation, contains 4 processes. Okay, the sum of all heat interactions. The problem they given sum of all heat interactions at minus 170 kilojoule per cycle. For one cycle, the sum of all heat interaction is minus 170. Then the system completes 100 cycles per minute. So per minute, how many cycles it is completing means 100. Suppose per minute, how much the sum of the heat interaction means minus 117 to 100, 17,000 heat interactions kilojoules per minute is there, summation of all. So summation of all heat interaction equal to summation of work interactions. There is no accumulation of energy. The change in energy of the cycle is 0. So this is the given data. Then complete the following table showing the method for each item. So whatever the 4 process is there, first we want to complete the unknown parameters. So we want to determine unknown parameters in each and every process. Next, and compute the net rate of work output in kilowatt. And compute the net rate of work output in kilowatt. Net rate of work heat in transfer we know minus 17,000 now only I mentioned per cycle into number of cycles per minute. For kilowatt they are asking kilojoules per second, not kilojoules per minute. Divided by 60 you will get the, so the second question we can answer easily. Move to the first question, we want to fill the unknown parameters. So each and each process, you select each process and apply the first law of thermodynamics for closed system undergoing individual process and determine the unknown parameters. Simple problem. The first process A to B, heat transfer is 0. Heat transfer is 0 means it is a reversible adiabatic process. It is fixed. Work done they given. So substitute heat supply minus work done equal to change in energy, or heat supply equal to change in energy plus work done. Then 0 heat transfer is 0. You substitute the change in energy is minus 2170 kilojoules per. Why? Because heat and work and change in energy, they are following kilojoules per minute. So that's why we following entire problem. We are maintaining heat transfers in kilojoules per minute only. Our process B to C. Here heat interaction is there, but work interaction is 0 in constant volume process. Constant volume process I already mentioned. Whatever the heat we are supplying, total heat will convert as a work only. Same. Then total work transfer is 0. Total heat we are supplying, total heat will convert as a change in energy. Simply a substitute, you will get the change in energy. Heat supply equal to change in energy. Third process, they given heat interaction, they are not given work interaction. We want to determine the change in energy. Then to substitute to determine the heat interaction they given, change in energy they given, we want to determine the work interaction. Then work interaction equal to 34,500. Next, D to A they are not given anything, but summation of all heat interactions per cycle given, per minute how many cycles also they mentioned. Determine the remaining unknown heat interaction. Summation of heat interaction minus 117 to 100. So 17,000 kilojoules per minute. Then determine the unknown heat interaction. And second one, change in internal energy of the cycle is 0 because the summation of all heat interaction is equal to summation of all work interaction. Determine the change in internal energy. Determine the change in internal energy of the D to A and substitute heat transfer and change in internal energy. You can determine the work done. But you can cross verify one statement, summation of all heat interaction equal to summation of all work interactions. In this cross verification also value must be come in the same value minus 53,670. Then fill the table. Then you add this all and add this all, it must be equal. If it is not equal, our process is, our calculation method is somewhere it is lagging. Next, rate of work output. Rate of heat transfer work output is same, minus 17,000 kilojoules per minute. But in the problem they ask kilojoules per second or kilowatt. So divide by 60, we will get minus 283.3 kilowatt. Simplest simple problem. So one more example I am giving for assignment purpose. You can solve. I double the values, that's all. Last problem they given 170. Now I given 340. Last problem they given number of cycles per minute 100, and now I given 200. All values I doubled just for practicing purpose. So these are the simple problems asking for closed system. Next, first law of thermodynamics or flow process. For non-flow process we completed, we solved some simple problems. Flow process means some mass is entering to the system and leaving from the system. There is a mass interaction. Boundaries are fixed boundaries. Boundaries may be real and imaginary. Through the imaginary boundary only mass is entering. Suppose every mass having the internal energy, we already mentioned. By our process, the internal energy may increase or decrease, secondary. But that mass want to enter into the system, it has to perform some work. Without doing work, how it will enter? And with the mass is leaving from the system, at that time also it has to work on some work on the surrounding. Then only the mass will leave from the system. So in a flow process, internal energy is not sufficient. The mass have the internal energy for entering or leaving from the system or to the system. It is performing some work. That work is called flow. So the new word introduced, Moiler, Richard Moiler. There is a flow process. Mass having whatever the mass is entering, it has internal energy plus some flow work is pressure into volume. So internal energy U plus PV is called some total heat, total energy like that. In a modern thermodynamics, when they introduced it at 1930, they give a name, that property name is called enthalpy. Okay. Last in closed system we already derived. Internal energy is a point function. Pressure and volume also point functions only. These all properties. Automatically enthalpy also property only. You don't want to prove that one. So enthalpy, internal energy plus flow work. Specific enthalpy, because this is an extensive property. Depend on mass. We want intensive properties. Just divide by mass. You will get a specific enthalpy, small h, small u plus p into v. This property we are using for flow process. That's all. Enthalpy, new word we introduced, that is enthalpy. That enthalpy we are using the flow process. These are already discussed. So we are applying now first law of thermodynamics for flow process, but in thermodynamics we are dealing steady flow. The property with respect to time is not changing in power plants or refrigerators. Any system thermodynamics, it's a steady. So we are dealing with only steady. So now I am applying steady flow process, first law of thermodynamics. So with mass, some energy is entering. So having the mass, having the some internal energy, having some pressure, having some volume, having some velocity, having some altitude. Next, living mass also having some internal energy, some pressure, some volume, and it is performing some work. It is our target heat. We are supplying some heat and we are producing some work. So total energy in equal to total energy out. So what type of energy is coming? Internal energy U1, flow work, pressure into volume, kinetic energy C1 square by 2, potential energy Z1 into G, and heat we are supplying. Output same. Work done, we are producing output, and living mass having some internal energy, living mass have some pressure, flow work, living mass having some kinetic energy, living mass having some potential energy. Then write the equation, steady flow energy equation. M into U plus internal energy plus flow work PV plus kinetic energy plus potential energy, and heat we are supplying. There is a energy in, energy out. With mass, some energy is leaving, some internal energy, some flow work, some potential energy, some kinetic energy, and it is performing some work. Rewrite already from 1930 onwards. This total energy we are calling as a enthalpy. M into H1 plus C1 square by 2 plus Z1 G plus Q equal to M into H2 plus C2 square by 2 Z2 into G plus work done. This is the steady flow energy equation. This equation we are applying all type of devices, work producing devices like turbines, internal combustion engines, or work requiring devices, compressors, vapor compressors, hydraulic pumps, superchargers, or no work devices like nozzles, condensers, boilers, cooling towers. So this steady flow energy equation we are applying for all devices. You can see nozzle condition, you apply the conditions. If there is no elevation difference, it is in a horizontal condition. You substitute the conditions, it is insulated, heat is zero, heat transfer is zero, and nozzle is not producing any work, just pressure energy is converted into kinetic energy. Then work done is 0. You substitute nozzle function itself pressure energy to kinetic energy. So initial velocities are low compared to exit velocity. So you neglect initial velocity, then you can determine the exit velocity. Exit velocity equal to C2 equal to square root of 2 into H1 minus H2. Enthalpy MCP delta T, then substitute that one. Finally, exit velocity you want to determine. Inlet temperature and exit temperature, you can determine the exit velocity of the nozzle. So simple. Like turbine also, it is also placed horizontal and there is a negligible velocity difference. Then it is in horizontal, there is no difference of head. Then you substitute the equation, it is fully insulated because all work interactions we are assuming adiabatic. Adiabatic is heat transfer is 0. Then you substitute the work done equal to m into h1 minus h2. But here always h1 is higher than h2, it is work producing device. Coming to the compressor, same we are applying, it is work requiring device, same conditions we are applying, but h2 always greater than h1, we will get negative value. Same equation, if you get negative value means we are work upon the system, if positive value work done by the system. We will solve some small problem. In a steam plant, 1 kg of water per second is supplied to the boiler. The enthalpy and velocity of water entering the boiler are 800 kilojoules per kg and 5 meter per second. The water receives 2200 kilojoules per kg of heat in the boiler at constant pressure. The steam after passing through the turbine come out with a velocity of 50 meter per second and its enthalpy is 2520 kilojoules per kg. Then the inlet is 4 meters above the turbine exit. Assume the heat loss from the boiler and turbine to the surroundings are 20 kilojoules per kg. Calculate the power developed by the turbine. And one more consideration they given, boiler and turbine as a single unit. So here mass flow rate they given 1 kg per second. Second, inlet enthalpy, inlet velocity they given. And heat supply they given. And exit velocity, exit enthalpy they given. But head difference they given. Inlet is higher than the exit. So head difference they given 4 meters. Z1 minus Z2 is 4 meters. And heat loss from boiler and turbine combined heat loss given. So heat supplied and heat loss. So first condition, boiler inlet, turbine outlet given. So boiler and turbine is a single unit. That assumption already they mentioned in the problems. Then we substitute, this is the given data, mass flow rate, inlet conditions. Then substitute, I want to determine the work done by the system. Move all exit with mass energy leaving, with mass energy entering minus mass energy leaving, plus heat supply minus heat rejection. In the problem they given heat supply and heat rejection. Then you can determine the work done by the system. Then work done by the system. But only one constraint you see, enthalpy in kilojoules, but velocity and head they are giving meters. So kinetic energy and potential energy will get in joules. So first you convert this joules into kilojoules, divided by 1000 kinetic energy, potential energy. Then substitute, you will get turbine means work done by the system means some positive value you will get. Otherwise you will get the negative value. One more problem. In the gas turbine unit, gas flows through the turbine. Same method. Mass flow rate they given and work done by the system is given and enthalpy of inlet and outlet they provided and velocity of inlet and outlet they provided. They are not provided head difference. So it is horizontal turbine. There is no head difference. You can remove that part in the steady flow energy equation. And work done they given. They asked heat rejection and inlet pipe diameter. For that purpose they given the specific volume of the inlet pipe fluid, specific volume they given. Then this is the given data. Then now I want to calculate heat transfer, work done from 1 to 2 process plus mass into exit enthalpy minus inlet enthalpy, exit velocity. Here also you see this one kinetic energy, it is in joules per kg. First convert into kilojoules per kg. Then only you can add. Otherwise, because work done in kilojoules per kg, enthalpy in kilojoules per kg, but this kinetic energy in joules per kg. you convert into kilojoules per kg. Finally, the heat interaction is minus 828 kilowatt. So in the problem also they asked heat rejection. Rejection means it want to be negative only. Ultimately we got negative value. So we are in right direction. Then they given specific volume of the gas at inlet, they given velocity of the gas at inlet, they given gas mass flow rate, they given the area of the inlet pipe mass into specific volume equal to velocity into area, means meter cube per second, meter cube per second you will get. You can determine the area we will get to 0.135 meters square. So simple problems. This problem. Next, what are the findings of first law of thermodynamics? Now we will discuss just what are the findings. First finding, heat supply minus work done equal to change in energy. Change in internal energy for closed system, change in enthalpy for open system. First finding. For cyclic operation, summation of heat interaction equal to summation of work interaction. These are the first finding. Coming to the second finding, isolated system energy is constant. Second finding. Third one, a perpetual motion machine of first kind is practically not possible. Without input, if any scientist came forward, I can produce output, means it is practically not possible. So these three findings from the application of first law of thermodynamics we identified. What are the limitations? In this they are not mentioned limitations. They are not mentioned directional feasibility. Suppose I will give some examples, then we will get the clear idea about the things. What is directional feasibility? Suppose I placed one cup of coffee in outside. Automatically coffee will cool. Why? Because outside atmosphere is low temperature, automatically it will absorb the heat. How much heat is absorbed means how much heat it is coming the thermal equilibrium condition. After reaching thermal equilibrium condition, you can calculate how much temperature drop of coffee is take place. That much of the temperature of the air is enhanced with mass flow rate MCP. But suppose by taking heat from the cold air, hot coffee, we can further heating is possible, because energy balance I can do, energy in, energy out. I am taking some energy from air, I will give the coffee. In paper I can give energy balance. Practically it is feasible. So that directional feasibility. One direction is only possible. Hot can cool, because based on the ambient temperatures. Or suppose electrical resistor is there. We are supplying electrical energy. It generates heat. Continuously it will generate. Suppose I am supplying heat to the electrical resistor, it will generate electrical energy. Energy balance I can do. I am supplying it so much of the energy I supplied. Energy in is the heat supply and energy out is electrical energy. By energy balance I can do. But practically it is feasible. The direction feasibility. Third one, Joule's experiment directly. By pedal wheel we are supplying some energy to the vessel. Very good. That work, that stirrer rotation, it is generating heat. Now I am supplying heat to the vessel. It will generate mechanical energy. In Joule's experiment also you see, they supplied work and they generated heat. Finally the given conclusion, summation of all heat interaction is equal to work interaction. But it is feasible only one direction, not two directions. Okay. So by this from these examples, one thing we can conclude, directional feasibility is first important for designing of the system. That is lagging in first law of thermodynamics. There is no, according to first law of thermodynamics, energy balance, that's all. There is no restriction on directional feasibility. So there is one data. Second, quantity. In first law of thermodynamics we are dealing only quantity. But in first starting of thermodynamics itself I mentioned different types of the energy is there. 1 kilojoules of the coal energy is not equal 1 kilojoule of electrical energy. Quality. Why? Because electrical energy directly I can use. If I want to use coal energy means first I want to convert to electrical energy. The conversion efficiency is 40%. So 40%, 60% reduction is there. So that quality and degradation of the energy, directional, in a different process, not discussed in first law of thermodynamics. So first what we are doing, first we are applying second law of thermodynamics for determination of the feasibility of the direction and quality. Once it is satisfied, then we are applying first law of thermodynamics for designing of the individual components of the thermal systems. Okay. So second law of thermodynamics, every student is confusing this point. Second law of thermodynamics we are not using for designing of the components, just for verification of directional feasibility and energy degradation. First we are calculating, applying second law of thermodynamics. If directional feasibility is accepted, then we are moving to the first law of thermodynamics for design. So designing of the all thermal systems based on first law only. But first law is not explained the directional feasibility. That's why we are applying second law of thermodynamics. So all spontaneous process in the nature occurs only in one direction. In other direction, they will not take place spontaneously and need some energy. Without energy input in opposite direction is practically not possible. In one direction, spontaneously it will take place. If I create a temperature difference, heat transfer will take place. Okay. So this is the brief explanation about first law of thermodynamics, application for non-flow and flow process. Thank you. Thank you very much.